Hello everyone, welcome back to another Math Olympiad geometry lesson. We are taking a leaf out of the AMC 10 and 12 review course that is happening at chinta.com. You can see details about it in the link in the description. In this recorded lesson, we will talk about the power of a point. As usual, we will pick up a problem and use that problem to learn the concept. If you are watching our videos for quite some time, you know that we always start with a problem and use that problem as a motivation to learn the concept, the underlying concept. We will do the same thing today. So pick a pen and paper and let's learn some outstanding mathematics together. So here is the problem. We have a triangle ABC and the side length AC is given to be 6, BC is given to be 3, E is a point such that CE is equal to 1 and AE is equal to 5. So we don't know where CE is. We don't know the location of E. So let's draw E somewhere. It's given that CE is equal to 1 and AE is equal to 5. Now you immediately should recognize something from this particular problem. That is, if you look at the triangle AEC, there is something wrong with this triangle. And what is wrong? Well, sum of two sides of the triangle is equal to the third side. But that cannot happen, right? It violates the triangular inequality. The triangular inequality. So what is the triangular inequality? The triangular inequality is that sum of two sides, sum of any two sides must be greater than the third side of a triangle. The only way this can happen if the point E is on AC. Then we would have C to E as 1 and A to E as 5. So the total value would be 6. So we should redraw this triangle. Let's redraw this triangle. So I'll make some space here. We have AC is equal to 6 and E is a point on that such that CE is 1, A is 5, BC is given to be 3 and we would join BE. Now there is a point F on BC such that AEB is equal to AFB. This is F. So AEB is equal to AFB. That is given. AEB is equal to AFB. Now the question is, well, actually the original question was something different. There was more construction. Let's do something simpler. We will try to figure out BF and FC. This is simpler than the original problem, which was somewhat of AMC standard. So American Math Competition is the first level of mathematical Olympiads in India. AME, American Invitational Math Examination, is the second level of mathematical Olympiads in US. AMC is the first one in US, AME is the second one. So the full problem is kind of like AME standard, but let's bring it down. Let's talk about only BF and FC. So the first thing that you have to use here is the cyclic quadrilateral property. Cyclic quadrilateral. How do you identify that there is a cyclic quadrilateral? So if you have a quadrilateral, how can you tell that all the 4 points, all the 4 vertices of the quadrilateral lie on the same circle? How can you tell? So one way to do it is, if you have a quadrilateral, draw the diagonals like so, and if these two angles, that is angle standing on the same line, this line, if the angles standing on this same line segment are equal, then we say that the quadrilateral is cyclic. Now I want to emphasize this fact because many students face a little bit of difficulty at this particular point. 2 angles are standing on the same segment if the legs of the angles are on the same segment. So the leg of this angle and the leg of this angle, they coincide. So they are standing on the same segment. So the angles standing on the same segment, we want them to be equal. What happens if they're equal? Well, that there is a theorem, and we are not going to prove it in this particular video, but there is a theorem that there is a circle that passes through all of these 4 points. In general, it is not necessary that all the 4 vertices of a quadrilateral should pass through the same point, same circle. It's not necessary that the 4 vertices are on the same circle. But in this particular scenario, that happens. Okay? So now we can apply this idea in our picture. Notice that here exactly that is happening. Well, it's not a complete quadrilateral. We have not sort of joined this F and E, but we could join it using a straight line. So then we have a circle, which is here. It's a circle passing through all these 4 points. That is the conclusion of the previous theorem that we just talked about. Right? Okay. So now that we have a circle, we can actually talk of power of points with respect to this circle. Power of points. So how are we going to do that? So what is the meaning of power of points? Well, let me draw a different picture. Suppose you have a circle and you have a point outside the circle. It could be done for points inside the circle as well. But suppose you have a point outside the circle. Then the power of the point P can be calculated like this. You draw a line that starts at P and cuts the circle at 2 points. Suppose this point is A, this point is B. A and B. Then the power of the point A, power of A with respect to this circle, this circle is PA times PB. PA times PB. Now, why is that true for any segment? That's the question you should be asking. Is there anything special about that segment, about that secant? Actually, there isn't. You could have drawn another secant, any other secant, and calculated px times py. It would turn out that px times py would be equal to pa times pb. If you drew some other secant, let's say like this, mn, then that would be equal to pm times pn. So we discussed in the AMC review course, and we talk about this in our Math Olympiad geometry module program, why this is true. There is some deep geometry going on. In fact, all of this is equal to square of the tangent. Square of the tangent starting at the point P and tangent to that particular circle. There is a nice visualization which you can use to think about it. This px times py becomes pa times pb, becomes pm times pn, and slowly you will see that these two pieces become equal in length. Like if you get a little bit closer, if I draw something like this, let's say this is J and K, then all of this is equal to Pj and Pk. Now both of these pieces, now they have started to become almost equal in size, and as you approach the point T along the circumference, moving along the circumference as you approach the point T, both of these pieces would eventually become equal and they would give you pt square. That's a dynamic way of thinking about what's going on. Of course, this is not a proof. The proof was discussed in the actual class, but we will not go into that. We will directly use that fact. So we want to find the power of the point C with respect to this yellow circle, and it is clearly CF times CB is equal to CE times CA. CE is 1, CA is 5, CB is 3, so you can now find out CF. So I would urge you to find out CF from this exercise. It's very simple, and put that in the comment section if you can find it out. This is a little challenge exercise, but the concept of power of a point is very useful in solving geometry problems from various Olympiads like IOQM, like American math competitions, like INMO, RMO, and so on. You'll be able to find more videos on power of a point in our YouTube channel. If you like this sort of content, please like, share, and subscribe. It helps us a lot. If you want to access our courses, go to chinta.com, check the link in the description to access the outstanding programs on mathematics, physics, and computer science at Chinta. Thank you for watching the video. I'll see you in the next one.